Hello everyone, I am Professor Shalini Sahay from EC Department, SIRT Bhopal. Today in this lecture, I am going to discuss the basic of transmission line. Transmission line, first we give the introduction. In an electronic system, the delivery of power requires the connection of two wires between the source and the load. At low frequencies, power is considered to be delivered to the load through the wire. In the microwave frequency region, power is considered to be in electric and magnetic fields that are guided from place to place by physical structures. Any physical structure that will guide an electronic wave place to place is called a transmission line. Then the types of transmission line can be categorized in the following ways. First is the two-wire line, coaxial cables, waveguides. Waveguides are of two kinds, rectangular and circular. Then planar transmission lines, which include strip lines, microstrip lines, slot lines, fin lines, coplanar waveguides, and coplanar slot lines. Analysis of differences between low and high frequencies. At low frequencies, the circuit elements are lumped since voltage and current waves affect the entire circuit at the same time. At microwave frequencies, such treatment of circuit elements is not possible since voltage and current waves do not affect the entire circuit at the same time. The circuit must be broken down into unit sections within which the circuit elements are considered to be lumped. This is because the dimension of the circuits are comparable to the wavelength of the waves according to the formula, where lambda is equals to c upon f, where lambda is the wavelength, c is the velocity of light, and f is the frequency of voltage and current. Now, the transmission line concept. The transmission line is divided into small units where the circuit elements can be lumped. Assuming the resistance of the line is 0, then the transmission line can be modeled as an LC ladder network with inductors in series arms and the capacitors in the shunt arms. The value of inductance and capacitance of each part determines the velocity of propagation of energy down the line. Time taken for a wave to travel 1 unit length is equal to Ts is equals to Lc to the power of 0.5. Velocity of the wave is equal to the 1 upon T. Impedance at any point is equals to Z is equals to V at any point upon I at any point. Or Z is equals to under root of L upon C. Line terminated in its characteristic impedance if the end of the transmission line is terminated in a resistor equal to in value to the characteristic impedance of the lines as calculated by the formula Z is equals to under root L upon C. Then the voltage and currents are compatible and no reflection occurs. When the line terminated in the short circuit line, then the end of the transmission line is terminated in a short. RL is equals to 0. The voltage at the short must be equal to the product of the current and the resistance. Line terminated in an open. When the line is terminated in an open, the resistance between the open ends of the line must be infinite. The current at the open end is 0. Now the reflection from resistive loads. When the resistive load termination is not equal to the characteristic impedance, part of the power is reflected back and the remainder is absorbed by the load. The amount of the voltage reflected back is called voltage reflection coefficient, and it is given by VR upon VI, where VR is the incidence voltage and VI is the reflected voltage. The reflection coefficient also given by this formula ZL minus Z naught upon ZL plus Z naught. Now the standing waves. A standing wave is formed by addition of incident and reflected waves, and it has no nodal points that remains stationary with time. Voltage standing wave ratio is Vx upon Vin. Then the standing wave ratio SWR in dB is given by 20 log 10 VSWR. The maximum impedance of the line is given as the Vmax upon I minimum, and the minimum impedance is given by V minimum upon I max, or alternatively Z0 upon VSWR. The relation between VSWR and reflection coefficient is given by the following formula. Now the general input impedance equation, where the input impedance of a transmission line at a distance from the load impedance ZL with a characteristic impedance Z0 is given by this equation, where B is called the phase constant or wavelength constant, and it is defined by this equation. Now the half and quarter wave transmissions line, the relationship of the input impedance at the input of the half wave transmission line with its terminating impedance is by giving as the L is equals to lambda by 2, and is the input impedance given by is equals to the load impedance. The relationship of the input impedance at the input of the quarter wave transmission line with its termination impedance by the letting L is equals to lambda by 2 in the impedance equation by this. Now the effect of lossless line on voltage and current waves. The effect of the resistance in a transmission line is continuously reduce the amplitude of both incident and reflected voltage and current waves. Then we will define the skin effect. As frequency increases, depth of penetration into adjacent conductive surfaces decreases for boundary currents associated with electromagnetic waves. It results in the confinement of the voltage and current waves at the boundary of the transmission line, thus making the transmission more lossy. The skin depth is given by the given formula. This is the application of the transmission line as a Smith chart. For complex transmission line problems, the use of the formula becomes increasingly difficult and inconvenient. So an indispensable graphical method of solution is the use of the Smith chart. Now, what are the components of Smith chart? The horizontal line, circles of constant resistance and conductance, and third one, line of constant reactance. The horizontal line running through the center of the Smith chart represents either the resistive or the conductive component. Zero resistance or conductance is located on the left, and infinite resistance or conductance is located on the right end of the line. Whereas the circle of constant resistance are drawn on Smith chart tangent to the right hand side of the chart and intersection with the center line. These circles of the constant resistance are used to locate complex impedances and to assist the solutions. Line of the constant reactance. Lines of the constant reactance are shown on the Smith chart with the curves that starts from a given reactance value on the outer circle and at the right hand side of the center line. This is the application or the types of the problems for which Smith charts are used to include the following: plotting a complex impedance on the Smith chart, finding VSWR, finding the admittance, finding the input impedance, locating the first maximum and minimum form, matching transmissions line with a single and parallel stubs. Plotting the complex impedance on the Smith chart, we can locate a complex impedance and admittance on the Smith chart. We can find the VSWR for a given load with normalized load and draw the circle with radius equal to the distance between 1.0 point and the location of the normalized load and the center of the Smith chart. The intersection of the right hand side of the circle with the horizontal line locate the value of VSWR. Finding the input impedance at any distance from the load, we can find with the help of the Smith chart. We can also find the power loss when an electromagnetic wave travels down a transmission line and encounters a mismatched load. Then there will be a power loss in the transmission line where the incident power is reflected back down the line, and this loss is given by this. There is also a mismatched power loss where we can define the mismatched power loss. These are the microwave components which are used to for the application transmission line. They can terminate the wave, split the wave, control the direction of the wave, switch power, reduce power, sample fix, transmit or absorb fixed frequencies. They can transmit power in one direction. They can shift the phase of the wave, detect and mix values. Then the coaxial components also there, which are includes connectors, coaxial sections, and the attenuators. Connectors, which are known as the microwave coaxial connectors, male and female. Coaxial sections are also there, where they can slip inside each transmission line while still making electrical contact. There are attenuators, which can reduce the power of the transmission line. Then coaxial cavities also are there, coaxial wave meters. Coaxial cavities are concentric lines or coaxial lines, whereas the coaxial wave meters includes the cavity to allow the transmission or absorption of the wave. Then there are waveguide components, which include directional couplers, T-junction, attenuators, impedance changing device, waveguide, slotted section, circulators, cavities, wave meters, filter, detectors, and mixers. These are the T's, which are kind of hybrid T junctions, which to split the waves from one waveguide to the other waveguides. There are different type of attenuators, which can reduce the amount of power of fixed amount. Types of attenuators are slide vane attenuators, flap attenuators, and rotatory vane attenuators. There are isolators, which are include mismatch or discontinuous, cause energy to be reflected back down the line. There are two kinds of resonator isolators are there: Faraday rotational isolator and resonant absorption isolator. Faraday rotational isolator combines ferrite material to shift the phase of an electromagnetic wave in its vicinity and attenuation vanes to attenuate an electric field, and that is parallel to the resistive plane. Whereas resonant absorption isolator are device that can be used for higher powers. It consists of a section of rectangular waveguides with a ferrite material, and which are placed halfway to the center of the waveguides along the axis of the guide. Thank you.